Hello,
Okay, hello sir, good morning.
good morning.
I'll just share my screen.
1 second.
So
Yes.
it's not, yeah,
Yeah, now
enabling. Hmm. So is my screen visible?
yes.
Okay. Hmm. Okay. So good morning everyone. The topic of our presentation is virtual functions and abstract classes. So I'll begin by telling you about what exactly are virtual functions, how they are useful, and how they are mapped by the compiler. So the concept of virtual functions basically comes from two very important OOP concepts, that is inheritance and polymorphism. And in short, inheritance is the capability of a class to derive some characteristics and properties from some other class. And polymorphism is basically the ability of a variable function or object to take multiple forms, to be implemented in multiple forms. So a virtual function employs both these concepts. Uh, by definition, it is a inheritable and overridable function or method for which dynamic dispatch is facilitated. Now, inheritable means that it can be inherited by a subclass. Overridable means that it can be sort of re-implemented in the derived class. And here, dynamic dispatch is basically the process of selecting which implementation of function to call, but at runtime. So, like if we have the same function in base class and derived class, which one is called is decided not at the compile time but at runtime. So this also implements runtime polymorphism, which can be like which we can see here as like a virtual function defines a target function to be executed, but the target might not be known at compile time. So this is basically implemented due to function overriding. So I know these are a lot of terms, but we'll be more clear with an example. So as you can see on the left, here we have defined a base class animal, which has a virtual function called eat, and it prints a statement. Now we have two derived classes called cat and dog, which derive from the base class animal, and they both too have this function eat, and they print different statements. Now what we do here is we have this function which takes in a pointer of type animal, and it calls the eat function. In the main, oh sorry, in the main function, we we define this pointer of class animal, and we make two objects of both of one of class cat and one of class dog. And first we assign the object of class cat to pointer, like the pointer points to the cat class object, and we call function. So what it does is it takes the pointer and calls the eat function from that pointer. So since this eat function is a virtual function, and since the pointer points to the cat object, so we see that the output is I am eating a rat. That is the eat function of the cat class. And the same thing happens with the dog object as well. When we use a pointer to point to the dog object and call function, it's printing I am eating a bone. Now, here are a few points to note here. So the first is that the virtual functions are called according to the type of the object which they point to or reference, and not according to the type of the pointer. As you can see here, like the cat object, the eat function of the cat object is called, and not from class animal. So, so in other words, we can say that virtual functions are resolved late and at runtime. So while without virtual function, if the function was not virtual, the keyword virtual wasn't written there, then the function call is according to the type of the pointer, like animal here. So if the virtual keyword wasn't there, then both these print statement that like both times this function was called, it would have printed I am eating food. So the second point to note is that here we see runtime polymorphism and dynamic dispatch at work. So at compile time, this function call here in line 22 is it mapped to either of the functions, and it is determined at runtime that whether the base class function or the derived class eat function is called. And the third thing to note is that we usually can use like derived class objects to sort of use to access the base class functions as well. And but here we are using a single pointer of the base class to access functions from different derived classes. So this gives us much more flexibility and ease while coding. Now we see that what actually happens behind the scenes. In case we don't have a virtual function, we see this in a very straightforward example. So here there's a base class called myBase, and it has a show function which prints a base class show function call. And then there's one derived class which also has a show function. As you can note that there's no virtual function here. So now when we, in the main function, now when we create a pointer of type myBase and assign it the address of the derived class object, and then call the show function, the compiler looks for the show function of type mybase, like here, and and maps this function call there at runtime. So it basically points this pointer when we assign this here to the object of the derived class. It points to the mybase portion of the derived class object. So even though we reference derived class object, the function from base class is called. So when we run this program, it will print base class show function is called, because here we haven't defined it as virtual. Now we see that what happens in case of virtual functions.
So Aditi, 1 second.
Yes.
So in the according to this, in the previous example, if we don't have virtual eat, if we don't have virtual void eat, instead of that, if we have just void eat, then the output will be both cases I am eating food.
Yes, sir.
Yeah. All right.
So now in case of virtual functions, the compiler maintains two things. One is called a V table, which is a table of function pointers maintained per class with virtual functions. And the other is a V pointer, which is a pointer to V table maintained per object instance. So every class that uses virtual functions or it is derived from a class that uses virtual functions is given its own V table. It is simply a static array set up by the compiler at compile time and contains one entry for each virtual function that can be called by objects of that particular class. So if, for example, if it's a derived class and its V table will contain functions from the base class as well, because it can access it.
Hello.
Aditi, are you there?
Does anybody who is your teammates? Do you have the slides?
Yes, sir. I'll present, sir.
All right.
Sorry, sir, my network just.
Okay.
Yeah, I'll just share my screen again. Yeah, I hope it's visible. So I was saying that a virtual pointer is just a hidden pointer which the compiler adds to the base class, and when it sees when it sees a virtual function there. So it also gets inherited by the derived classes, and when the class instance is created for any class, then the virtual pointer is set to automatically point to its V table, the class's V table. So the rule which is followed while populating the V table is that the entries in the virtual table point to the most derived version of the function which the objects of that class are allowed to call. So it just stores the function and the address, like the function which has to be called by it, the address of that version of the function, and it is always the most derived version of that function. So here's an example. So as you can see, there's a base class here, and it has two virtual functions, function 1 and function 2. Then there are two derived classes, class D1 and class D2. So D1 has this like re-implementation of function 1, and D2 has re-implementation of function 2 in it. So here you can see what happens is, because there are three classes and all of them have virtual functions, so there are three V tables that are set up, one for each class. And the pointer, the compiler, sorry, adds also a hidden pointer to the base class, which points to the virtual table of the for the base class here. And D1 and D2 also derive this pointer. So it says inherited, and they point their pointers point to their respective V tables. So each V table has two entries, one for function and one for function two. And each entry is filled out with the most derived function on that object of that class type. So we can see here that like for D1 in the V table, the function 1. So the most derived version of the function is in D1 itself. So here it points to the function in D1 itself. While the most derived version of function 2, which D1 can call, is in base class. So it points to the virtual function 2 in base class. Similarly, for D2, the most derived version is in D2 for function 2. So it points to the function 2 in D2, while the most derived for function 1 is in base. So it points to that in base. Now imagine that we make an object of class D1 and assign its address to a pointer of type base, like we did in previous example. So we have a pointer of base class and an object of D1 class, and we assign the address of that pointer, of that object to that pointer. So it is true that this pointer will only point to the base portion, to the base class portion of D1's object, like we saw previously. So it will only point to the base class portion. But as we saw, VPTR is only there only like it is also inherited. So it is also present in the base class portion only, and it points to the virtual table of D1. So now if we call function 1 using this pointer, it recognizes it as a virtual function and looks it up in the virtual table of D1. And since it is mapped to D1's function 1, then it is only executed. So I hope this is clear. Now I would like to call my friend Siddharth to explain virtual functions in C++ in more detail.
Hi everyone. So I'll be explaining how exactly virtual functions are implemented in C++. Now some of these points Aditi has definitely covered, but she had covered it quite briefly, and I'll be explaining more examples so that it's quite clear. So, but before jumping into virtual functions, let's have a detailed look at non-virtual functions and how they're implemented. Then later on, we'll see how virtual functions actually make a difference. So on the left-hand side, we have the code, and on the right-hand side, we have the output for that code. Now have a look at that code. There are two classes, base class and a derived class. The derived class inherits from the base class, and each of these classes has just one function named print, and the signature of both of these functions is identical. And also note that virtual keyword has not been used in the base class or in the derived class, and hence both of these are non-virtual functions. Now, in the int main, we have 6 different function calls, which are divided in 6 different cases. And I'll be going through each of these cases and I'll explain how exactly the binding of these function calls with the correct function definition is done. So first, cases 1 and 2 are quite simple. In case 1, if you see, an object of base class is created. The print function is called. Now the compiler sees the type of B and it finds that it's of type base. So it's quite clear that at compile time, the compiler will bind this particular function call in line 20 to the print function of the base class. And similarly in case 2 also, the print function of derived class is called as the compiler sees the type of the object D, and it is derived, so the derived class function print is called. Now case 3 is slightly different. In case 3, a concept known as object slicing is taken into use. So here base B1 is assigned D, and D is an object of type derived. So now I'll explain what object slicing exactly is. So have a look at the brown and green diagram on the right hand side. So every derived class object is of type this, that it has some derived class members which are defined by the derived class itself, and some base class members which are common to all the objects of all the derived classes which inherit from that base class. So in line 25 of our code, when we do base B1 assigned D, only the green parts of the object D and variables of the base class. Hence, finally, B1 is a variable of type base, and it has nothing to do with any of the derived class members or functions. So now in the next line, b1.print is again a very simple case where the compiler, based on the type of b1, binds this function call to the print function of the base class. Now coming to cases 4, 5, and 6. So cases 4 and 5 are quite similar. The base pointers b2 and b3 are assigned derived class objects. So, and after that, b2 arrow print and b3 arrow print are executed. So now here, the thing is that, as Aditi also mentioned, in case of non-virtual functions, the type of b2 and b3 would be looked at, and not the actual type of the object that these pointers are pointing to. And based on the types of, so these types of b2 and b3, the print function of the base class would be called, and not the print function of the derived class. And finally, the sixth example is also quite similar. And here also we see that b3 is as earlier, b3 is a base pointer, so b3 arrow print calls the print function of the base class. But if we had done d1 arrow print, then the compiler would have looked at the type d1 and called the print function of the derived class instead of the base class. So yeah, I hope that's clear. We'll move on to the next slide. Aditi, next slide, please. Yes, yes. So now I'll be explaining virtual functions and its proper implementation in C++. But before diving into the code, we'll have a look at some of the key points which are needed to understand how exactly this is done. So first detail is that if a function is defined using the keyword virtual in the base class, then all the subsequent functions defined in the various derived classes with the same signature are also virtual. So, okay, so for this example, the code on the left hand side is the exact same code that as we had in the previous slide, except that here in the base class, the print function has been declared as virtual. So there's a virtual keyword present out there. The rest of the code is same. So what this first point that I described earlier says is that the print function of derived class is also virtual, because this class derives from the base class, and print function of the same signature in the base class has been declared virtual. So all the subsequent derived class print functions with the same signatures would also be virtual. Then the next thing is, so when a virtual function is called, the compiler sees the virtual keyword, and such functions are bound late at runtime. So here, so unlike in the previous slide, where all the function calls were actually bound to the correct function definitions at compile time, here in the case of virtual functions, late binding or runtime binding is done. So I'll just more formally explain what late binding is. So in late binding, the compiler adds code that identifies the actual type of the object whose function is being called at runtime, and then matches the call with the right function according to that type. So yeah, that is what is late binding. In the previous slide, if you remember, we were always looking at b1, b2, b3, and d, which were actually either pointers or the references which were used to call the function, and we were not actually looking at the type of the object to which the pointers were pointing, for example. So but here, in case of runtime binding, we will be looking at the actual type of the pointer, actual type of the object. So I'll just also explain what early binding is, which happened during the entire previous slide. So in early binding, the compiler directly associates the right function definition with the function call at compile time using the declared type of the pointer or reference, as we were doing in the previous slide. Yeah, I hope that's clear, and we'll move on to the next slide. Okay, so this is the exact same code as we had in the previous slide. Here also we have all the 6 cases, and I'll be going through each of them. So in case So first of all, the first thing to note is that both of the print functions here are virtual, as I explained earlier, and hence all of these print calls, function calls, are actually going to be bound at runtime, because they are because the compiler understands that they are being used to call uh, some virtual function, so it decides that a late binding would take place. So now in cases 1 and 2, it's very simple. As at runtime, the actual type of the object is looked at, and in case 1, the actual type whose print function is being called is the object is of type base class, and so the print function of the base class would be called. And in case 2, the print function of the derived class would be called, because the actual object type is also of the derived class. So these were very straightforward cases. Now in case 3, as we have seen earlier, object slicing takes place, and finally b1 is of type base only, and there is no variable or function in b1 which is defined in the definition of the derived class objects. So here also b1.print is bound to the print function of base class at runtime. Finally, 4, 5, and 6 case in these cases, the so when the print function is being called, the pointers are of type base, but at runtime the actual object is looked at, and based on its type, the function calls are bound to the correct function definition, and hence in all of these cases, that is 4, 5, and 6, the print function of the base class would be called. Okay, I hope that's clear. Yeah, next slide. Yeah, so here's another example. Here the code is slightly different. So we have again the base class and a derived class, and in the base class there's a private virtual function named do_f. Note that it's virtual but private, and we also have a public function which is not virtual, and its name is f. And in class derived, we have a public non-virtual function named do_f. This is non-virtual because the function do_f in the base class is actually private, and so it is not inherited by this derived class, right? Yeah. So now also note that in the f function in the line 8, the f function is actually calling do_f of the base class. Okay. Yeah. So now in the main function, we have first created a derived class object d and a base pointer bp, and that bp is assigned the address of this derived class object d. So now when we call bp arrow f, so this particular function call is bound to the f function of the base class at compile time itself, because it is not a virtual function. That's the first thing. Now at compile time, the compiler sees that f function is calling do_f, and so what it does is it decides that this do_f, which is a virtual function for the base class, is actually a virtual function, right? So it needs to be bound at runtime. So it doesn't bind this particular function call in which is present in line number 8 to the definition, to any function definition. Now what happens at runtime is that bp arrow f calls the function present in line number 8, f function, and the do_f call in that f function in line number 9 actually binds to. So now what is left is that the actual object type is looked at runtime, and the actual object type, as we can see in line number 21 and 22, is of class derived. So based on that, what will happen is at runtime, the class derived would be looked at, and a function with the same signature as do_f, which is present, same signature as the call of as present in the line number 9 is there. So it will be checked in the derived class, and it finds that do_f is present. So finally, instead of calling the do underscore f of the base class, the derived classes function would be called. So yeah, this is what happens in this one.
It's a very convoluted example, yeah.
Sorry.
Because uh, I don't know if this behavior is specified by the standard C++ standard, uh, because it's such a complicated example, this one, yeah.
Sir, actually, I got this example from C++ documentation itself, I think.
Okay.
Yes, sir. Yes, sir.
All right. Yeah. But you didn't explain this typecasting of object slicing. I think that plays a very important role in all three examples you presented, because you are taking a, so usually what happens in that, what happens is that in C, C++, etc., you have the typecast of, I can take a character and typecast it into an integer. I can take an integer and typecast it into a float, and so on. C++ also allows a derived object to typecast to its base object, base class. That is what you call object slicing. Yeah, so you take a object of type derived class, and then you cast it into an object of type its base class. Now, all three examples which you said, in which you take an object and cast it into a pointer or a variable of its base class, and then you checked what happens in the base class. I mean, that is exactly what we call by, that is exactly the behavior we call runtime polymorphism in C++. Okay. This precise behavior you just described, but yeah, but yeah.
So I will be doing that in Java, in the example of Java.
Pardon?
I will be explaining that in the example of Java.
All right, all right. No, continue. I was just I mean, reflecting whatever came to my mind. Yeah.
Yes, sir.
But very good example. Very good example. But it's unlikely that in real life you will ever encounter such things. The runtime polymorphism, the dynamic dispatch, is quite useful because it allows you to dynamically create dynamically specify object behavior. This is the same this thing in Haskell also. This is exactly how they implement parametric polymorphism in Haskell. Another thing is that, did you talk about pure virtual functions, or is it coming?
Sir, it will be coming.
All right, all right. Okay then. All right, continue. Thank you.
So hello guys, I'm Ankit and I will be explaining you about the virtual function in Java. So we saw a lot of C++ and a lot of virtual keyword everywhere where it was being implemented. So the thing is that in Java, there is no virtual keyword. In fact, all the functions or methods are virtual by default. Before seeing this example and explaining it, I would like to remind you that in Java, all primitives like C++, all primitives like int, car, etc. are similar to the primitives of C++, but all the non-primitives are always references. What do I mean by that is that whenever we make an object, whenever we declare an object of the of primitive type, the object is declared in the same way that the object is being declared in C++. But whenever we define a non-primitive object, that is the base class or the object of base class or derived class, it is actually being declared by reference. So that is the one of the properties in Java. So let's see this example. So in this example, in the base class, the print function is virtual by default, and in the derived class there are two functions: the print function which is there in base class, and another loan function which is not there in base class. In the main function, what I do is in the case one, I declare I declare an object of type base, and it is being pointed by the reference of type base only. And in case 2 also, the same thing happens for derived class. So the case 1 and case 2 are normal classes, and B and D are references of the object of the same type. What happens in when we call the print function in case 1 and case 2, you can see that the base print and the derived print is being called respectively, because the type of the object and the type of the reference is same. But in the third case, the third case is an example of upcasting that Sir was telling about, that the pointer is of type base, but the object is of type derived. And whenever upcasting happens, all the functions which are actually just there in derived but not in base, those functions or variables actually get removed from the object, and you can't use them while calling them from the reference, that is B1 in this case. So so when I call that B1.print, it prints that derived is the print of derived is printed, but and also we can see that whenever I print B1, it is showing that it is a pointer of type derived. It is an object of type derived. But if I call B1.loan, that is the function which is there in derived but not in base class, and B1 is an object of type base, is a reference of type base, it will give out an error because there is no method of name loan in base class. So that is the main functionality of virtual functions in Java. Aditi, can you please go to the next slide? So the next thing that came to my mind was, okay, if virtual functions are the default function type in Java, so what are the how do you use the non-virtual functions? So it depends on what do you mean by the non-virtual functions. If you search on the internet, the standard definition is that the non-virtual functions just does not allow the derived class to override the function method in the base class. So on the internet, the simple answer is use static methods. But the thing is, whenever we use static methods, we cannot use any variable of non-static type in that method. To use the static methods, we just need to change. We just need to add a keyword static in the definition of the method, as you can see in the example on the side of it. And so, what if you want to use non-static variables all in the method? So what you do for that is you use a final keyword. So what final keyword does is it does not allow the derived class to have a function of the same name as the base class. And you just add a final keyword instead of the static keyword, as I told in the previous case. You can see the example in the side of it. And so the thing is this method, that is a final method, is not exactly the same implementation of non-virtual functions in C++ in case of Java, because in C++ you can have non-virtual functions, and you can also define another function of the same name in derived class. But in Java you can't do that. If you do that, it will just give out an error. So that is how you use non-virtual functions in Java, and the exact implementation is not possible. So to conclude on virtual functions, I would like to say that the key points to remember is that virtual functions are implemented based on runtime polymorphism, and a type of reference and object decides which function is to be called. That is, during the early binding or compile time binding, the type of the reference matters, and during the late binding or the runtime binding, the type of the object matters. Also remember that whenever object slicing or upcasting occurs, all the functions and variables of the derived class is not there in base class when we upcast it. So that is the key point to remember. The difference is that in C++, the default function type is non-virtual, whereas in Java, the default function type is virtual, and the exact implementation of non-virtual functions of C++ is not possible in Java. So that's it for the virtual functions. Now I would like to call Sudarshan to carry forward this presentation with abstract classes.
Yeah, thank you, Ankit. And now I'll be talking about abstract classes. So basically, an abstract class is conceptually a class that cannot be instantiated. So we cannot create an instance of an abstract class, and is usually implemented as a class that has one or more virtual functions. So basically what makes an abstract class is the presence of a virtual function. So basically if there is a virtual function in a class, then it will be considered an abstract class. So we use abstract classes because sometimes the implementation of all or some function is not known. So thus the class which inherits the abstract class has the implementation of the virtual function. That is, the function is overridden in the class. So here we see an image. We see entities person, player, and coach. So here we observe that player and coach are being derived by person, which means that player and coach have the characteristics of a person. And similarly, the soccer players has characteristics of a player, but the person alone would not know the characteristics of a player and coach, and hence we use inheritance uh, through virtual functions. So basically, what a person would have some similar like similar some functions which can be implemented by player, but would not know the exact implementation for player or coach. So they will be overridden, and hence the player will add its own implementation. So yeah, next slide please. So abstract classes can have a body. uh, they can have constructors, concrete methods and non-concrete methods, and variables too. But we cannot create an object of an abstract class. So yeah, we cannot create an object. So in Java, we also have a reference type similar to similar to abstract classes, which are called interfaces. So basically, what an interface is, it since in abstract classes we can have some implementation, right? We can have some concrete methods, we can have a body, we can have variables too, but in interfaces we have only the declaration of methods, which is it is generally an empty class with only pure virtual functions. So yeah, abstract classes have limited inheritances in Java. So basically, there are 5 types of inheritances, which are single, multi-level, hierarchical, multiple, and hybrid. So in C++, we can implement all these types of inheritances, including multiple and hybrid. But in Java, we cannot implement multiple and hybrid inheritances because multiple inheritance is sort of like not a very good implementation. So basically, what happens in multiple inheritances, more than one base classes are used to derive a derived class. So this is not a good implementation, and because if two base classes have different implementations for a method, and then we derive a class on the basis of those two classes, then we would not know which and if we create an object of that derived class, we would not know which function to really call. So that is sorted out in Java by using interfaces. So what interfaces would have basically is the function declaration only, and no no implementation. So we add implementation in the derived class, and then we can sort it out basically for multiple and hybrid inheritances. Yeah. So next slide, please. So here we see why we cannot create an object of an abstract class. So basically what happens when an abstract class is created, a virtual table is assigned for that abstract class. So when we create a pure virtual function in an abstract class, we reserve a slot for a function in the v table, but we don't put any address in the slot. So the v table will remain empty, and as the v table is empty, then the compiler will not let the creation of object for such class, and it will simply display an error message whenever we try to do so. So yeah. So now, thank you everyone, and now I would like to call Yuvraj to talk about abstract classes in C++.
Thanks, Roshan. So to move to abstract class in C++, we first need to learn about pure virtual functions. So pure virtual function is simply a virtual function for which we do not have an implementation in the class, and we declare it by assigning 0. So in this example, in the right side, we have a class shape which is having a pure virtual function get area, and the syntax for declaring pure virtual is by assigning 0 to it. So in this example, virtual void get area equal to 0 will declare a pure virtual function get area. And we will come back to this example later, but let's first now look about abstract classes in C++. Aditi, next slide. Okay, so by definition, an abstract class in C++ is a class that has at least one pure virtual function, and the classes inheriting this abstract class must provide a definition for the pure virtual function. Otherwise, the subclass would become an abstract class itself. And to understand the importance of abstract class, let's look at this example. So let's consider we have an parent class animal, which is having a pure virtual function speak, and we have three subclasses, cat, dog, and duck, which are inheriting from the base class animal. Now this makes our abstraction easily that we can add more animals, but all the animals will have some sound which will be different, and this is where we need abstract class. So in this example, the virtual function speak, pure virtual function speak will be implemented in the subclasses cat, dog, and duck, and they will provide implementation of their speeches respectively. So basically the use of abstract classes C++ is when we don't know the implementation of a function in the base class, but we can provide the implementation in the inheriting class. Now let's look at outline of abstract class in C++. So in this example, we have a class base, which is having a pure virtual function show in line number 4. Then we have an inheriting class sub, which is inheriting base. And in this class, we had not provided the implementation of the pure virtual function show. So this class will be treated as abstract as well. Now we have another class derived, which is inheriting the subclass, and we had provided the implementation of the function show here. So we can create an instance of this class. So in the int main, in line number 26, we have base, we are creating an instance of class base, which will cause an compile time error. Similarly, creating an instance of class sub will cause an compile time error because class sub will be treated as an abstract class. Although we can create an instance of the class derived, and also we can declare pointers of the class base as well as class sub. Also note in C++ that we can use the pointers of the base class to point to the derived class and call the functions, virtual functions of the derived class. So to summarize this slide, we have a base class having a pure virtual function show, and the base class will be treated as abstract. And if the abstract class does not provide definition of all the virtual functions, then it will be treated as an abstract class as well. And we can create object of a derived class only if it provides a definition of all the virtual functions present in the base class. And finally, in the C++, the pointer of the abstract class base can point to the derived class here, and we can call the implementation of virtual function using these pointers. Now let's look at an example of abstract class in C++. So consider that we have one class shape, and we are having two subclasses rectangle and triangle. And we need to define a function area that returns the area of the shape. So the function cannot be implemented in the class shape because the formula for area is different for different shapes. So we need a pure virtual function here, and the class shape will be implemented like an abstract class. So the deriving classes can provide implementation of their respective areas. So let's look at its code. So in this code, we have a abstract class shape, which is having a pure virtual function area. And we are having two setter functions, set width and set height. So we are talking of some limited shapes, and the variables width and height are protected here. Next slide, Aditi. Now in this example, we have two subclasses, rectangle and triangle, which are inheriting the base class shape. In the rectangle class, we had provided the implementation of area as width into height, and in the triangle subclass, we had implemented area as width into height by 2. And also note here that just like Aditi told you in virtual functions, we are declaring a function that returns the area when we provide a pointer to it. So the use of this function is that we don't need to provide separate functions for each of the subclass. We can use the base pointer to call the area function of any of the derived class. It will be more clear in the next slide. So we are declaring a pointer of the class shape. We are creating two objects of class rectangle and triangle, and we are using the setter functions to set width and height of rectangle and triangle. Now in this example, we are using the pointer of the base class to call the area function of the derived class rectangle, and similarly we are using the pointer to call the derived class function of area of triangle. So finally, when we call these functions using this pointer of the base class, we can call the derived class function, and the output of the code will be the area of rectangle is 50 and the area of triangle is 80. So this is where abstract classes are used in C++. Now I hand over to Viransh to take you through abstract class in Java.
So thanks, Yuvraj. So now I'll talk about some brief points of abstract classes in Java and discuss them with some of examples. So the first point is that a class is called an abstract class in Java if the class is declared within keyword abstract, and it can have abstract as well as concrete methods in it, and is described in this example. We are declaring the class shape as an abstract class because there is a keyword abstract before the declaration of the class. Next slide. So yeah, as we have seen in C++ also, we can't instantiate the abstract classes. So for that we have to make an derived classes, and as we can't make the direct objects of base classes, we have to make instances of derived classes, and then we can call the functions in it. So here in this example, I'm creating the base b, and I'm assigning it as a implementation of derived class, and then I'm calling we are calling the methods of derived class, and this will be executed and the output will be derived function is called. Next slide. So yeah, in C++, we have seen that for abstract classes, we have to make one virtual function in that, but in Java, if we don't declare any abstract method in the parent class, so that will be also fine. So in this example, we can say that there is no abstract method in the class abstract class base, but this code will be compiled and it will be run successfully, and the output will be base function is called. So next slide. And the last point is that we can also have constructors in abstract classes, and these constructors will be executed whenever the instance of derived class will be created. So in this example, we can say that the derived class base, in derived class, in base class base, there's a constructor called base, and this constructor will be executed whenever whenever we create the object of derived class. So output will be, first of all, the constructor of base class will be called, and after that constructor of derived class will be called. So base constructor called, and then after that derived constructor called. So now I will talk. I will discuss some comparisons. I mean similarities and differences, and after that we'll conclude our presentation. So there are mainly two similarities in C++ and Java, that in both we can have constructors, and this constructor of abstract classes will be called whenever the instances of inherited class is created. And also we need to override and define the abstract methods in the child classes to run the programs in C++ and in Java both. And the main differences are that in C++, for a class to be called abstract class, we need to define at least one pure virtual function using virtual keyword. But in Java, we can also create the abstract class by calling abstract keyword only. And the another main difference is that in C++ we can't have any abstract class without any virtual methods or abstract methods. But in Java we can have abstract classes without any abstract methods in it. So yeah, that is it for abstract classes in Java. Thank you
So much. It was a fantastic presentation. Uh, any questions? I don't think anybody has any questions.
So I had a question.
Yeah.
So with reference to, I think one of the slides that Siddharth Shah presented, in which the doF function was called.
Mm-hmm.
So in that, the second one was declared public, while the first one was declared private in the base class.
Yeah.
So if we essentially removed the implementation within the derived class, then it would throw an error on line 23, right?
If we do what?
If we remove 14 to 16, we don't have any function in
Yeah, it will throw an error.
It will
So
throw
what happens is that so imagine even if you don't have any virtual thing going on here, okay? Imagine you have a function doF in base and a function doF in derived, and what will happen is that whenever you have you do a derivation, the derivation in the definition, the derivation will mask the base ones. Okay, so for instance, imagine derived has this doF function which is private. Okay, and doF in base is public. Imagine that. So right now, doF in base is private and doF in derived is public. Let's imagine the other way. DoF in derived is private. DoF in base is public. Now, if a third class, a class which is not derived, which is an object which is not derived, or you call from within main, if you call BPROF, okay, what will happen? It will not take the doF of derived, it will take the doF of base. Am I making sense? Hello?
Yes, sir.
So that's because this will be happening at compile time, no? The binding.
The binding will, yeah, that one will happen at the compile time. But in this case, runtime polymorphism happens at the. So my point was simply that you have certain rules, and about how do you find the correct for each method. There is, like you said, there is a table of methods, and then you search in that table about what is the definition I should take. That, yeah, and yeah, I think I confused a lot. Anyway, my point was that there are both features in C++ about selecting which method to run of an object. Okay, and that decision is taken sometimes during the compile time, sometimes during the runtime. And in fact, sometimes what happens is that you cannot have all the decisions about which method to run cannot be taken at compile time. Yeah, that is very clear, that which method to run, you cannot decide at the compile time. So what happens is that for every object, there is a list of methods it can run. I mean, it has access to, and during runtime, what will be taken is that the latest method out of that list of methods will be taken. Okay, that's exactly how operator overloading also happens. One second. Yeah, so in operator overloading also what happens is that you have multiple definitions of a method, and during runtime you select what is appropriate one. Okay, so to answer Devani's question, if there was no method in 13 to 15, then during compile time it will be detected that the BP doesn't have access to, so the main doesn't have access to a function called do underscore f, which is in f, and therefore there will be an error. I hope I made some sense. Any other question?
Sir, can you repeat that?
So what I was saying is that if the question was that what will happen if I don't have a function do f in a class derived? Okay, so what will happen is that the compiler will detect that there is no do f which has a public access from main. And there will be an error. Can somebody verify this? Maybe don't take it my word on that. I hope the compiler will be smart enough to detect that. But in the real C++ compiler, I mean, they should detect it ideally, because this is something which you got which you should have access to. Yeah, because I mean, this can be statically verified, whatever this. I hope is there any other question? All right. I don't think we have time for the next presentation. It's 1 hour. So let's have it some other day. This week itself, some other day. So tomorrow we will meet again at 10:15. All right. Thanks, everybody.
Sir, I had a question.
Yeah.
Sir, like we try to this is the second group. So like for today's presentation. So sir, we try to stick to the time limit of 25 minutes, but we can also make a detailed and elaborate presentation like this. So can we make a elaborate presentation like this then?
Yeah, please go ahead. No problem.
Okay, sir.
Yeah. Yeah. So the thing is that yeah, I mean, C++ is a very complicated language. Like I said, it allows, its philosophy is that we will allow everything, we will subsume everything. That's the philosophy of C++. So that is why that whatever is there in any programming language in the world is there in C++. Yeah, I mean C++ subsumes everything. See, Java, Haskell, everything. That's their philosophy. So therefore, what happens at the same time is that most programming languages disallows things for very good reasons. For instance, Java does not allow multiple inheritance because it cannot coexist with virtual functions. Yeah. If I mean, unless you want to, otherwise you have to have all kinds of things like public derivation, private derivation, protected derivation. All these kind of things has to be there. So that's why Java restricts the possibility of inheritance to limited, and then chooses what is appropriate definitions. C++ does not do that. It allows everything, and therefore most things are complicated. And I mean, you cannot always say that whatever it is instructive in a sense. Yeah, the sense that instructive in the sense that it you look at how C++ do something, and then you have a feeling. Then it may not be that it should be that way. Yeah, I mean, you get what I'm saying. Like it's not instructive in the sense that you don't get a good feel of how things should be. Yeah, I mean, but if you look at Java or Haskell or Lisp or something like that, then it allows the freedom of doing things. It restricts the freedom of doing things, but it restricts to it selects what are the best ways of doing things and then restricts to that. C++ philosophy is the other end. It doesn't have any restriction. Everything is allowed, and it is up to you to choose what is the correct design, which is not a good idea. Yeah, because good designs come from restricting the possibilities, the choice of possibilities. Okay, that's what is good design. I mean, no. Absence of that's what actually is design is. Yeah, it's actually selecting this narrow subset of things is what is called good design. So yeah, so but the things what are important in C++, this thing is the idea of pure virtual functions, the abstract classes, and the dynamic dispatch, the runtime polymorphism. It is yeah. So today we touched upon those things, but the upcasting and things like that, yeah, it is also important. Otherwise, you don't have dynamic dispatch. But this example of do F and F, I don't find it very instructive. But I mean, if you want to understand C++, you should certainly understand such examples. But otherwise, they are not very instructive in the sense that such kind of scenarios rarely appear in daily practices. Okay, but if you want to learn C++ as a language, then definitely you should look at those such examples. Okay, so my point was that yes, we should look at we can have detailed presentations, no problem. Okay, we will find days. We still have 2 more weeks to go, so not a problem. Okay then.
Sir, I have a doubt.
Yeah.
Sir, is the content from these presentations going to be there in the maybe final exam syllabus?
Yeah, yes. The final exam will be based on C++.
Okay, sir.
All right. Okay then. Thank you.
Thank you, sir.
Bye.